Okay, good morning, everybody. So I will be dealing with DFT plus U, which is what I mostly develop, and I'm very happy to speak after Boris, so that I don't need to convince you of the importance of strongly correlated materials in the study of the Earth's interior. Also, he highlighted the need for developing a computational tool that is flexible, reliable, and easy to improve, and who's powerful enough to produce results that are easy to interface or to compare with experiment. I think this need has been very well highlighted even yesterday with integrated people talking about their experience with both experiment and calculations. So today I will present DFT plus U, which is one of the simplest approach you can have to deal with strongly correlated system, and we'll try to highlight what it takes basically to develop a computational tool that is easy to use, user-friendly, reliable, and you can easily put behind a web interface, for example, and have a broad community of users able to use it, able to trust it, able to trust its results, and able to extract from its result basically quantities that are easy to compare with experiment. So this is the outline of my talk. I will go through a brief introduction on what strong correlation is, okay, and then we'll illustrate a typical example, multi-insulator, and also present briefly how DFT plus U tries to overcome these difficulties, and then we'll highlight basically these needs and what we're doing to try to build such a computational tool that is reliable, flexible, and predictive enough to be useful for this community. What strong correlation, static correlation was introduced briefly yesterday by Don Trula, and I will go over it very quickly this morning, starting from the example he was mentioning yesterday, which is basically the hydrogen molecule. If you have an hydrogen molecule, you think to see how the electronic state evolves from the helium atoms, where you have the two protons collapsing on each other on the same nucleus, you will realize that the most difficult situation is the intermediate distance one, where you have basically the molecule, okay? And it's easy to realize that if you construct an anti-symmetric wave function for the two electrons in the system using only one Slater determinant, you end up with terms, okay, so-called ionic terms that are the ones describing a configuration with two electrons on the same site, whose weight shouldn't be as large, or whose weight should change with distance, okay? Those are the terms that you want to see to be killed with when the distance between the protons is increased. Now, this is not easy to obtain, okay, with using only one Slater determinant. Okay, if we had exact DFT, that wouldn't be a problem. They would be able to do that, although it's based on a single Slater determinant representation of the density of the electronic density. This is so because the exchange correlation functional that Don Trula was talking about yesterday would be able to kill, I can't see this type of terms in the electronic wave function. Now, writing a functional of the charge density that does that, and then implicitly does that, is not that easy. So DFT plus U is a way to help, it's a correction that helps the exchange correlation functional killing these terms, okay, and localizing the electrons on either side in the case of the hydrogen molecule. Now, is this kind of effect important in solids? Yes, it is, especially if you have localized states, okay, where the electrons tend to like D states or F states, where the electron tend to localize, not because of the scattering on nuclei, but because of electron-electron interactions. Those are called Mott insulator, and prototypical system in this class are transition metal oxides. So with one-to-one stoichiometry, like in this case, this can be manganese oxide or iron oxide, anything. So they have rock salt structure with rhomboidal symmetry due to magnetization. And iron oxide is certainly one of the worst cases, in the sense that in GGA, one of the standard DFT functional is predicted to be a metal instead of an insulator, as it's observed from experiments. So you see Fermi level cutting a D manifold here, and the reason is that the downspin electron is sitting on almost triply degenerate set of states, of D states. So how do we try to take care of these kind of problems? Well, many body physicists have already their own model that's called the Hubbard model. And here is a very simple, minimalistic expression for this model. So you see that you have a kinetic part, a one-body term of the energy, that is this first term here of the Hamiltonian, which is proportional to the Hoping amplitude. And then you have this term, the on-site interaction, that discourages, that is an energy penalty, okay? This U is a positive parameter, and then it's an energy penalty for having double occupation of the same atomic site. So this is how, basically, we discourage double occupation of atomic site. And the idea is to embed somehow this model that is the classical reference model for treating strongly correlated system in the DFT Hamiltonian. Of course, we will need to use this part, while on this other part DFT does quite well, so we don't need to touch it. The idea is to add a functional that is modeled on the Hubbard functional and take out something that is already contained to avoid, in DFT, to avoid a double counting problem. Well, I won't go through every detail. The final expression that we normally use for this corrective functional is given in here in a somewhat Hartree-Fock-like fashion. And we compute those occupation numbers by projecting the constant state on localized orbitals. A simple approximation to that corrective functional gives us this final energy functional, where you see that the correction is proportional to this parameter U, and is a trace of n times 1 minus n. So it's a penalty that is introducing the energy for having occupation different from 1 or 0. Okay, so you basically are discouraging a partial occupation of atomic orbitals, so discouraging basically hybridization with neighbor sites. And here is just a demonstration of how it works. If you extract the potential acting on the wave function, you see that it's attractive if the state is almost occupied, is repulsive if it's almost unoccupied. So a gap is open between the occupied and unoccupied states, and the size of that gap is approximately of the size of the is approximately U. Okay, so formally this works, and this is demonstrated already by the case of iron oxide. So this is what I was showing you before, and this is what we obtain in comparison with this correction. So we can open a gap. The gap is the right order of magnitude, and we're quite happy with our results. Of course, this is a parametric correction that we have introduced, and you easily understand, and the strength of this correction depends critically on the value of this parameter here. So in order to obtain a reliable approach, we need to have an idea how to evaluate this number here. And I'll briefly go over our approach that is based on linear response for obtaining this number. So basically, this U parameter is can be evaluated as the second derivative of the energy profile as a function of the occupation, atomic occupation. Okay, so in fact we have that once we apply a correction of this kind, if U is this is the curvature of the DFT energy profile, you would get a straight piecewise straight behavior for the energy, which is exactly what we expect, especially in the case of unisolated atoms in contact with a reservoir. And the features that we're recovering is exactly the band gap. Okay, so Don Trullo was mentioning yesterday that the band gap is a difficult feature to obtain. So this is an easy way to reintroduce an easy trick to reintroduce this feature into the quantum spectrum. And how to evaluate the second derivative? Well, this is a little bit tricky. We use linear response theory, which means to have a separate calculation of this parameter, and then before you can use it in actual calculation for production run, basically. There's been the ability to compute these parameters has been quite important, and iron oxide is truly an example. So we discovered that there is a broken symmetry phase, for example, that is that was obtained distorted in the 1-1-1 plane of irons, and is able to reproduce in much better agreement with the experiment the rhomboidal distortion of the unit cell as a function of pressure. So in contrast with what is sometimes believed in literature that GGA can still predict good structural properties in spite of the fact that the gap, for example, is not well reproduced. We see here that account for strong correlation is very important for structural properties as well. And I have more evidence for that later. Here's another example that was actually developed in Renata's group about the calculation of transition pressure, the spin transition pressure in MgFeO. And again, the ability to calculate U and as a function of volume or pressure in both spin state was critical for obtaining this result. A more recent example of that on lanthanum cobaltite was worked out by another postdoc in Renata's group very recently, and shows the importance to evaluate this parameter actually consistently with the structure. So what one should do is to evaluate the U, does a relaxation with that U, re-relax, recompute the U, and re-relax until structure and electronic parameters converge with each other. So here's the second problem now, flexibility. What if we want to use this in general? So Boris was mentioning that DFT is good to make prediction across the periodic table. That's problematic indeed. And what if we now can believe that we have something that works for transition metal oxide or a correlated system somehow? I mean, it's not perfect, of course. What if we try to use it for simple things, like silicon, for example? Well, it turns out that if we do it blindly, it doesn't really work. Actually worsens the results of standard approaches, okay? As you can see, for example, these three columns are the equilibrium lattice spacing, the bulk modulus, and the band gap in electron volts. So you can see if we add if you add the plus